Thank you very much for having me. My name is Steve Chua, and this talk has been entitled 4 hours ago. I wasn't quite sure exactly, the content was there beforehand, trust me. It was just, I was shaping the title at as the last step. So I decided to call it Music Information Retrieval Using Locality-Sensitive Hashing. This is a data science crowd. I guess you guys are adept with numbers and algorithms and such. So I think this may be of interest to you. Some more acknowledgements. Thank you to the SF Data Science Meetup organizers for allowing me to speak today. Perhaps we did enough product placement with O'Reilly, but here's some more. Thanks a lot for sponsoring this event, so I wouldn't have to pay hundreds of dollars myself to feed you guys. I'm sure you're great people, but I'd rather have someone else pay for me. Special thanks to Jay LaBeouf, who's sitting here. Why don't you wave your hand, Jay? He's right there. So Jay is the reason I came to San Francisco. I worked for his company named Imagine Research. I'll tell you more about that later. And a lot of the material that you see here today is presented as part of a workshop down at Stanford's CCRMA, Center for Computer Research in Music and Acoustics, also known as CARMA. And we're trying to do a little bit of outreach, kind of bring some of that material to the general public outside of an academic scenario. Parts of this talk were also prepared with the assistance of my colleague at HumTap, Owen Campbell, who's a master's student at UCSB. So speaking of Stanford, so that's Jay. You may not be able to tell, so this is the workshop, and there's a wonderful Adobe Air demo of music recommendation, the most beautiful Adobe Air demo I've ever seen. Here we're presenting the MediaMind audio web recognition engine, audio recognition engine. And this is another photo of us. There's Jay, that's me, down at the workshop. So just as a little plug, we do this every summer for 1 week in June or July. If you're interested, feel free to go to the CARMA website and learn more. Tiny bit about me. I spent my first 18 years in New Jersey. Anyone here from New Jersey? Yeah, woo, yeah, New Jersey, yeah. We're in New Jersey. Okay, my dad worked there. I'm also from North Jersey. We should hang out later. So I spent my next 11 years at the University of Maryland. And are there any Terps here? No? Terp? Oh, nice. Yeah, go Terps. Exactly. We should hang out later. So there I studied computer engineering and electrical engineering. Did my dissertation in an area of music information retrieval, known as music transcription. And in 2011, I came here to San Francisco to work with Jay and his company called Imagine Research. And there we were trying to build a web-based audio recognition engine. Something kind of like Shazam. Have you heard of this app Shazam? It's on your phone. And if you don't know what piece of music is playing over the restaurant loudspeakers, you just open up Shazam and you hold it up for 5 seconds and it'll tell you that this is Billy Joel or something. We were trying to do something similar to that, but more for general audio. So perhaps it's something that can tell you, is this the sound of a tennis match, a baby crying, an explosion, jazz music, female speech? So you can imagine it's a lot broader problem, less constrained, and in many ways far more difficult. That company was then purchased by another company called iZotope in March of 2012. iZotope makes audio processing software, and they're located in Cambridge, Massachusetts, just north of MIT campus. I left there in June of 2013 to pursue some of my own independent projects, and I joined HumTap in 2014, earlier this year. So what is HumTap? We are making an app that makes it really easy to make music.
Hello, I'm Thomas from HumTap.
And I'm Jan from HumTap.
Think about 30 years ago, you needed a big, expensive studio to record a song. Today, you can have all that gear in a laptop.
That's why many people say that everyone can make music nowadays. But the truth is, you still need a lot of knowledge and you still need a lot of gear. But what if you could just hum a melody? Like bum ba da 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 ba da da dum bum bum ba bum 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 ba da da da,
And then have someone else tap a beat.
And finally, you select a genre.
And that's all you need to create a little tune. Now, personally, I'm more into electronic music, so let me change the genre and see what we get.
That is enough.
You can also hum a different melody.
One might imagine. How does it do that? How does it go from the audio domain into the symbolic, the musical domain, all in relatively real time? Well, that's what I work on at HumTap. So that is one example of music information retrieval. What exactly is music information retrieval? Well, I'd like you to listen to this very closely and tell me all of the musical attributes that enter your mind related to this excerpt.
When you pay the rent, did you think that money was heaven sent? Friday night arrives without a suitcase.
Yell out everything that you can tell me about that piece of music. Anything you know.
Descending baseline.
I'm sorry?
Descending baseline.
Descending bass line?
Chord progression.
Chord progression, do you know specific chord progression? Blues. Okay. Yeah.
Ones and fives.
Ones and fives, right?
There's a dude singing.
Like keep it at that level. There is a male vocal in the foreground. English language, thank you. Two drum beats and a hi-hat. How many, what drum beats specifically, aside from hi-hat? Bass drum. Bass and snare, at least, I think, right? What key was it in? Anyone? No one know?
Major probably.
I think it was maybe A major. I'm not quite sure. Time signature. 4/4. What about tempo? Tempo, anyone? Like beats per minute? I think it was roughly like 100, 110, 104 maybe. Anything else? Did we cover all the instruments? Guitar, right. Guitar. Yeah, I think was there a piano? Yeah. Okay, so can you imagine? Okay, one more example. Same question.
Classical.
Classical genre. There's a piano and there's a violin. Sorry, louder.
18th century?
That's actually 19th century. Does anyone know the composer? Beethoven, thank you very much. What piece is it? The Spring Sonata, first movement. Very good. What key is it in? Oh, you're almost there. No key? F major. Time signature? 4/4. Anything else? What mood is it? What? I'm sorry? It is in F major, right? But just what sentiment, what mood, just adjectives, yeah. Cheery, yeah. Calm, yeah, I'd say so. So think of these labels that you just came up with and try to program a computer to do that. It's very difficult depending upon what task it is. Maybe to do some of the more quantitative or low-level tasks to identify certain notes. Maybe it's easier, maybe it's not. But then how do we assign cheery and calm to something like this? There's a lot of machine learning and interesting algorithms going on beneath the hood. So MIR is a very broad interdisciplinary area of research that covers areas such as computer science, engineering, mathematics, physics, psychology, biology, psychoacoustics, music, musicology, music performance, history. And as far as tasks, these are just a sample. Audio fingerprinting. Tell me exactly that this is Beethoven being performed by Pinchas Zukerman, to give me the exact recording. Cover song detection. Tell me what composition it is, but it can be a different recording, a different instance of that composition. Is it genre? Is it classical? Transcription. Get me every single note event. Recommendation. If you like Beethoven's Sonata No. 5, you might also like Sonata No. 8. Symbolic melodic similarity. Not just in the audio domain, but in the symbolic domain, as if you're looking at sheet music, can you decide if melodies are similar? Onset detection is a low-level task that's very important. Just give me the beginning of every note. It's harder than you think. Mood, is it cheery, calm? Source separation. Imagine being able to separate the piano from the violin, and then you can do with that as you please. Is there a piano and a violin? Pitch tracking, being able to follow the contour. tempo? Is it 100 beats per minute? Score alignment, so audio domain, and imagine you have a piece of sheet music. It sure would be nice to have something that tracks the symbolic domain, the sheet music, as a piece of audio is playing. Song structure and form. If you have a piece that's ABA, say sonata form, it would be nice to identify those verses and which ones are similar. Beat tracking to follow the beat, the toe tapping rhythm of the music. Key detection, is it in F major? Query by humming. If I just say da 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 da, if a system can actually retrieve that, that's query by humming. And then query by tapping, imagine just remove pitch, but you just say. That's not as well researched. So don't worry about that too much. So it's not just an academic exercise. This is actually very pervasive in industry these days. These companies that you see here, Pandora, Rdio, Adobe, Shazam, YouTube, copyright detection, Gracenote, Isotope, SoundHound, they at one point in time did a sort of a query by humming, query by singing. Echo Nest, which was recently purchased by Spotify. Melodyne, which is arguably at this point perhaps the best pure transcription commercial software out there, but certainly leaves some room to be room for improvement. But this is just not anymore within the top universities. It's being slowly entering industry with the improvement of computing resources and the combination of musicians and algorithmicists and engineers. Okay, so that's MIR. What is data science? No, seriously, I have no idea what data science means. I like this article's tone or style may not reflect the encyclopedic tone. Yeah, that's because I think a lot of people have difficulty coming to a standard definition. I love this Venn diagram here. So this is from Wikipedia. And so if you're doing math and statistics and you have expertise in an area, but you can't hack, then that's traditional research. But a combination of all three, that's data science. But if you don't know math or statistics, but you can hack and you're good at something, like watch out, you better mess something up. Yeah, I don't know. There was really no point to that slide. I just thought I'd poke fun at that a little bit. Okay, so MIR. Those tasks that you saw earlier often follow a very common workflow as far as the solution. Let's take, for example, mood classification. In comes a piece of audio, and maybe it's cheery or calm or angry. And somehow, an audio signal, which can be represented as just one long array, a one-dimensional signal, is a lot of data, perhaps too much. And somehow, you'll have to map that signal onto a feature space and represent it in that feature space somehow. Maybe the piece of audio is in stereo, and you'll need to bring it down to mono through downmixing as a pre-processing stage. So that's what you do with segmentation and pre-processing. You're going to take your piece of audio and you're going to frame it, say at frame sizes of 50 milliseconds, 100 milliseconds. And for each one of those frames, you're going to extract a set of features. And those features collectively represent the input audio. So those features, which we'll talk more about later, are chosen depending upon what problem you want to solve. If maybe we're doing genre recognition, you might want to take a feature that's more timbre dependent. If we're doing transcription, perhaps you might want pitch information. Finally, once you have all of those features, we'll apply some area of machine learning, whether it's supervised or unsupervised. Say in this case, a supervised machine learning algorithm, we would feed with pieces of audio that are cheery, and we know through ground truth that it's cheery or calm, and we would train something like an SVM or otherwise. And then with a novel test example, it would go into the model, and that is how we know that a piece of music is cheery or calm. So as far as the specific machine learning algorithms, that's not something I'll really focus on here. You can learn more about deep belief networks, that specifically at like any meetup talk these days. So this one is not going to talk about neural networks at all. Sorry to disappoint you. SVMs, k-nearest neighbor, k-means, and so forth. But you'll see more examples later. So that's the architecture of a system diagram. We need to feed it with data if we're going to do something like supervised machine learning. What data do we use? Well, you have a lot of choices, and data is definitely a problem in music information retrieval. Because when we're doing MIR research, music inherently is something that is regulated, like by law. Like you can't just publish a bunch of commercial music that's on an album and distribute it to everybody. That is illegal. So you have to be careful with certain, use audio that is distributed under a research-friendly license, or in some cases, say such as these data sets here, they may not actually include the original audio, but rather just some derived set of features and ground truth information that will hopefully suffice for you to solve your research problem. So if you were to Google, say, for audio content analysis data sets, you'll find this entire page, just a portion of which is here, and you'll find a lot of interesting data with which to work. So that's what you can train and evaluate on. So let's make this a little bit more concrete. I also don't like to be paralyzed by PowerPoint, and so we have some exercises ready for you today. Exercise. It's funny, when you do a Google image search for the word exercise, there's a lot of interesting stuff that comes up. Okay, let's see if this works. Okay, so I have a bunch of demos, and I need you to expect that it's not gonna work. So your expectations are like really low. So I'm just showing you something called an IPython notebook. These days, Python is what I usually do in my day-to-day job. And yeah, IPython is kind of like, for those familiar with MATLAB or Mathematica, it's like the desktop in MATLAB or a notebook in Mathematica in the browser. So here we have a piece of audio. Sounds like this. So 5 beats, kick, snare, kick, kick, snare. And this talk won't focus too much on the Python particulars, but I'll just mention briefly that this example uses a library called Essentia, which came out of University Pompeu Fabra in Barcelona, Spain. It has Python bindings to, in this case, load an audio file into an array, which I'm calling simple loop. And then what we can do next is, I mentioned feature extraction and segmentation. For every frame in the audio called simple loop, we'll compute certain features. Well, what features can we compute? Well, we have a lot of choices. In this example, I'm computing something called the zero crossing rate. The zero crossing rate is literally how many times the input signal crosses the horizontal axis. Let's make this a little bit more concrete. Okay, I'm sure I can do this. Let's escape and B. So let's plot simple loop. No. Oh, because I have to run the thing. Okay. Okay, loaded. And there we go. So this is literally the signal. And there you see a bunch of drum beats. Let's zoom in a little bit. Let's just plot the first, whatever this is. Sorry. So there you see that the kick drum at the beginning oscillates slower. It has more bass component than the snare drum. And so perhaps we might expect its zero crossing rate to be lower than that of the snare drum. So indeed, if we did then plot, sorry, I'll scroll up in a moment. I'm going to plot the features column by column. So what I'm doing here is I'm plotting all of the zero crossing rates for each frame in that signal. It may be a little bit hard to see, but you'll notice that there is some non-negative zero crossing rates right over here. And you'll see for the snare drum, it shoots up. Okay, well, let's look at the other feature, which I believe was energy. Okay, interesting. So we see some energy, and if you, it may be a little bit hard to see, but if you look at the temporal profile, the envelope over time, you'll see some common, common shape between the 3 kick drum beats and the 2 snare drums. So that might motivate us to say that a combination of those 2 features in a 2-dimensional feature space should suffice to classify those beats. So indeed, let's try to do that. What we're going to do first is just scale our features, which is a good idea because your features may be computed using a variety of different scales, and depending upon your machine learning algorithm, that could be a bad idea if you feed that into the model. So this will just scale all of our features to be between -1 and 1. And here, let's just plot in the 2-dimensional feature space the zero crossing rate versus the energy. And indeed, this is what we get. So maybe does this match your expectation if, bless you, if we have a lot of silent frames, maybe they have no zero crossing and no energy. Maybe there are some loud frames, but their zero crossing rate is low. Those could be the kick drum. And then some high zero crossing rate, but not as loud, and that could be the snare drum. So indeed, if we were to run k-means clustering, which does not require any training, all it is doing here is clustering each frame using, in this demo, a predetermined number of clusters, 3. We do see, do you notice a little pattern here? Here, kick, snare, kick, kick, snare. And that's all there is to it. So with those labels, we can then replot the scatter plot. And indeed, we see that it does cluster all of, in this case, the kick drum beats, frames, the snare drum frames, and the silent frames together. So hopefully that makes that a little bit more concrete as how a typical MIR system works. So that's one example. Let's look at another example. Music search and retrieval. So it's a very important problem in music information retrieval. It's not like query by tapping. That's not important. Search and retrieval is pretty important. And this talk was entitled MIR Using Locality-Sensitive Hashing. I was motivated to focus on that. You'll see why in a moment, but also that I overheard it at one of the previous data science talks, I think over at Yelp when someone from YouTube was talking about video recommendation, and he mentioned locality-sensitive hashing. So I think that's an interesting thing. Many of you may find that to be somewhat interesting. What is locality-sensitive hashing? It is an algorithm that addresses the approximate nearest neighbor problem, meaning that in the nearest neighbor problem, we have a bunch of points in a space, and given one novel point in the space, I want to find which training example is closest to the test example. So all you have to do is go over the entire training points one by one, compute their distances, and find which distance is smallest. That is very slow. That is complexity that is linear in the size of the training set. The approximate nearest neighbor problem tries to reduce that complexity from linear to sublinear, something that is at least less than linear. We don't know exactly how much less than linear it is. It may not be logarithmic, but something that is less than linear in the size of your training set. The term locality sensitive means that if you have any 2 points in your feature space, and if they are close to each other in the feature space, then it is very likely that they have the same hash. A hash is just a reduced representation of data. Compare that to what you might be familiar with as a cryptographically secure hash. That is the complete opposite, where you have 2 points, and if you just make the smallest distortion, perturbation, in between one point versus another, then a cryptographically secure hash is designed to have dramatically different hashes. This is different, and this is better suited for, say, multimedia applications. When you have a frame of audio and another frame of audio that's a little bit distorted, the audio content is still the same. And therefore, if we're going to use this to extract the identity of a piece of audio, then we want the algorithm to allow for those distortions. Locality-sensitive hashing does that. It works well in high-dimensional spaces. It is easy to implement. That's another important point. And its theoretical complexity is well studied. I'll mention what exactly this hash function is in a moment. But basically, what this is giving more rigor, mathematical rigor, to what I just mentioned a moment ago. If you have 2 points that are close to one another, then it is statistically likely that their hashes are the same. And if they are far apart, then it is likely that their hashes are different. So this is an example in a 3-dimensional space, constructing an LSH table using 4 bins. Each point is one training example or dictionary atom. And indeed, you will notice that all of the blue squares are clustered together. So if they are close together in the feature space, which is what you're looking at, then their hash identity, which is denoted by which marker it is likely to be similar. Okay? So how do we use LSH? Well, to query the system, what comes in is just a feature vector in the feature space. You compute some hash function, which again I'll mention in a moment. And that hash function is just like a binary string, a bit string. That information goes into a table just to do a hash table lookup. You'll just look for the bin, which has key 110100, and it'll get whatever information is in that bin. And being that this is done over an entire signal, you will need to do this once for every single feature vector. And so somehow you'll have to aggregate this information and do some ranking afterwards, depending upon what your application is. I should mention that LSH is used in a variety of ways. This is not the only way you need to use it. And in fact, the application that we'll see in a moment does not strictly do approximate nearest neighbor, but it does do search and retrieval. So the other side of the coin is table construction, which is like training. I'm not using the words training and testing because it's not really training, but you have to construct the data structure. And so through all of your training audio files, you'll do feature extraction, and they should have an associated ground truth label. You compute the hash, and that, along with its label, and perhaps the feature vector itself, goes into the hash table. So that's how you make the table. Okay. So you're wondering, what is this hash? Well, don't be too scared by the LaTeX font. I'm trying to keep it as simple as possible, and there won't be too many of these slides. So to compute the hash, just looking at this equation, where's my cursor? Here. Oh, no cursor. Okay. What all you have to do is take, for an input feature vector Q, you're going to do random projections, meaning that for our our novel point Q, we're going to take just a whole bunch of random inner products, denoted in this case by P, and we're going to just see, is Q aligned with P or not? Namely, is it on like one side of a space defined by Q or not? So sign just means if that inner product is positive, return +1. If it's negative, return -1, or 1 and 0, something like that. So I said random projection. Random in what sense? Well, you can literally just take these vectors Q, which are just Gaussian. Zero mean, unit variance Gaussian, just it's embedded into most programming languages these days, independent, and that's it, really. Like, you don't need to do much more than that to compute at least one bit of a hash. So why Gaussian and why random? Well, there's what this is just saying is that with that choice of random projections, it can be shown that you will hash together points whose angle in the space is low. So on one extreme, if you have 2 points which are completely aligned, have perfect correlation from the origin, then they are 100% likely, using this hash construction, to lie in the same hash bin. If instead they are completely opposite, so -1 correlation, then there is 0 probability that they'll be in the same hash bin. And so in between, if, say now looking at this here, if you have 2 points that are 90 degrees apart, then, so 90 degrees means like pi over 2. So it is 50% likely that they'll be in the same hash bin. Okay? And so that's just for a single bit. We're going to do these inner products, one for as many bits in the hash that we want. If we want a 5-bit hash, you'll compute 5 projections with the input vector q. And so that is, man, no cursor. That's okay. That is denoted here by little k, 5. We want a 5-bit hash. So what this is saying, and furthermore, you don't need just a single hash table. You can have several hash tables denoted by the variable L. Let's make that 3. So you have 3 hash tables. And what this is saying is that we define 2 hashes to be the same if for at least one table, all of the bits in the hash match. So the entire 5-bit hash matches for at least one table. If that is true, the reason we allow multiple tables is because it kind of generalizes the space a little bit better. Being that this is random, there may be some projections that aren't good, but their contribution kind of gets decreased or amortized if you use more tables. And finally, to construct the table, to construct L tables, as mentioned, you just do one projection for each of the 5 or k bits, and that's your hash. Okay. So, live demo. This is what comes up when you do a Google image search for demo. Also in an IPython notebook, I've put together just some code that does LSH for music search and retrieval. What I have in a training folder are a bunch of audio files that, let's see if this works. Okay, sounds something like this. Let's do this. Or this. Or let's do this. And there are roughly, how many of them? Like 30 or something, 40 files in this demo. So, okay, define a hash function. In code, in Python, this is really all there is to it for the hash function. You'll do a dot product or a projection between a bunch of random Gaussian vectors and your input vector. And if they lie on one side of the space, then you set that bit to 1. And don't worry about this function here. We're just converting like 100 to the integer 4. So here's an example. Okay, I think I already ran this. So if I just did this over and over, we see that this hash function creates a bunch of integers between 0 and 15 because I have vectors of length 512, and there are 4 of them. And so x, in this case, is like a novel feature vector. And we're projecting that against the matrix called projections. Yeah, sure. Question.
So what if your projection vectors, don't you want them to be closer to orthogonal to get the most information out of them?
Yeah, absolutely. That's a great question. The question was, wouldn't you want your projection vectors to be close to orthogonal so you get more information out of them? Think in an extreme case, if you have 2 projection vectors that are the same, then they don't add any additional information. Being that every single element, in this case rand n, is independent and identically distributed, I don't want to say something stupid, but I think it's likely that if they're long enough that they should be, in the long run, in the average, orthogonal, using, in this case, rand n. Or it's probabilistically low that they would be correlated.
The vector has 512 elements, is what you're saying?
Yes.
Okay.
Is that what I'm saying? I think so. But that's the point that you're making is that you're not guaranteed that every projection vector will add more information, and you're absolutely true. There's nothing to guarantee that that's not the case. You're absolutely right. Okay, great point. So in code, how do we actually write LSH? Well, I'm going to show you 3 structures, one called table, which is like one LSH table, then an LSH structure, and then one that's actually the audio part of it. And I'm not going to do a full code review with each of these cells, but it's nothing more than these 3 cells to be able to do that. So starting bottom up, first, just like to point you to this query function in a table with these 3 lines here. For a vector, you compute its hash, and if the table has that key, then just return what's in that bin, as we said earlier. And as we said for table construction, once again, you compute a hash, and if that bin already exists, you insert the label and perhaps the vector too. This is just an implementation detail. I ran out of memory, and I don't think I really need this for this demo. But this would be vector, and you would add that to the bin denoted by the hash h. Okay, that's it for table. And then what I call here class LSH, and by the way, there are a ton of Python LSH open source libraries out there. I just wrote this for pedagogical purposes, but don't use this. So you initialize a list of tables with particular dimensions. And then if you want to add a vector to one table, this is how you do it, and you do it over every table. And then you just query for each table in the structure. Now finally, for what I call music search here, what I've decided to do for this demo is for features, all I'm going to do is take the actual spectrum of an audio frame, as in like the nearly full spectrum. So it's not like we're taking zero crossing rate or energy of the frame. No, we're just going to take 1,000 or 2,000 FFT bins from the spectrum and use that full thing as our feature vector. It sounds insane, right? But you'll see that it works in a moment. And then some other details, which you can ask me more about later. But since it's 7:43, I'm going to go ahead and train the system. Or first, what I'll show you with the results that are already canned and here on this page, that with this test file, which I'll play right now, Okay, that wasn't very good. Sorry, both the clipping and the playing. Then you'll see that here in the results, these are the top results, and let me play this for you. So that first one is, and I promise you I'm not BSing you. So that's partita number 3, first movement, the beginning. And let's see the second result. Okay. So, since it did say live demo, let's try with a different piece here. And I'm warning you, I may have some memory leaks and crashes, so I may need to restart this a couple times. Okay, so let's play the test file. Oh, yikes. Okay, that was terrible. So this one didn't work as well, but the best match is the piece that you actually heard is this one, and then I think that is the only and this one as well. Let's do piano. Let's do that one. Okay, let's play Brennan 01. So indeed, that is what comes up here. Okay. Can someone tell me what this is? Anyone know? Composer? I think that's Brahms. Let's see what happens. So indeed, so 1, 2, I think those are the only Brahms Rhapsody representatives. So I thought I would try some tests of my own, using a violin I brought today. So let's see if this works. And okay, let's do, okay, so I'll record 10 seconds. Okay, and then
Keep going.
I'll do more if this works. I'll have to put it down because that's expensive. Okay, so that's, I called it test.wave. And that was Bach Partita number 3, first movement, the beginning. So the best match is here, this one. Let me try Beethoven Sonata number 5. Okay. Okay, now I named it test.wave again. Okay, so we'll run that. Let's hope we see Beethoven Sonata number 5. This one, yeah, so this one is actually the best match, or that's the piece of music. I'm sorry? Yeah, they are. Okay, so that one, and then this one, the beginning, is also a match. And let's try Bach Sonata Number 3. It's all that this can do, so for the live demo. Sorry. That was a little bit too long. That was 18 seconds, and these excerpts are like 10 seconds, but we'll see what happens. So we'll run that again. Oh, yay, okay. Fantastic. I'm sorry? It was Bach Sonata Number 3, the third movement. Yeah.
Bar for live demos.
It's just saying I expected it to not work, and I'm glad that it worked like 50%. That's fine. So I should mention, okay, so for that Beethoven excerpt, which I will play the training sample, Beethoven Number 5, let's say by Bingo Zuckerman. Okay, so listen. There are two instruments. I just played one, and it matched so-so. Okay, let me just try one more. I'm going to play this. Which I actually have here. So this has 10 instruments, or 3 different parts. I wonder if I use the right training file. So with being that this is a Baroque piece, sometimes when they play it in the Baroque style, they'll play it a little bit lower, like a half step lower. And that would really change some things when it comes to machine learning. But let's just see what happens. Okay. Okay. This I'm expecting to not work, but. Thank you. So that was again in test.wave, and that's Brandenburg Concerto Number 3. Let's see what happens. Okay, it's number 7. Okay, there it is. Yeah. But you heard 10 different people playing there. Of course, please do.
So, have you analyzed these results and figured out why it's off, for example? I mean, what's the weighting factor?
Great question. Can anyone suggest how this can be improved? So this was just for demo purposes, and you may have seen some kind of poor decisions, some flawed decisions here. Is there anything else we can do? Say maybe use better features?
Well, what's the quiz?
Yeah, that's right, and you passed. So perhaps we can use features that are more appropriate for whatever task we're trying to solve, something other than the full spectrum. Because if you have the full spectrum, if you're just off by a little bit, that means it's going to bin completely differently. Also, the choice of the number of tables and the hash size are things that can require some trial and error, for lack of a better word. So there are a lot of ways that you can improve this. I hope you don't take this to be like the ceiling of what LSH can do. There's a lot more engineering involved to improve that, but definitely there are varieties of this. And I'd be happy to talk more about that offline. So the time is now 7:53. I am going to find my presentation, live demo. I don't think I'll talk much about non-negative matrix factorization, which is why I put it at the end of the talk, just in case there was time. I don't think there is, but if you're interested in non-negative matrix factorization, how it can be applied to music transcription or even music recommendation, feel free to talk to me after the talk. I have some IPython notebooks here that deal with it. Okay. The question was, what is the most determining attribute that zeroes in on what piece of music it is? That depends highly upon your task. I think if you're doing, say, cover song retrieval, you may want to use something called the chroma vector. That encapsulates melodic information, but not at too fine a level, not too specific, because if you have two different people playing the same work, then there will be some acoustic differences, but mostly musical similarity. And a feature representation like the chroma vector has just the right level of specificity. So that's what you would use for cover song detection. For maybe genre recognition, you might use timbre. You might find certain instruments just present in rock and not in jazz, some in classical and not in reggae. So it depends highly upon what problem you're solving. But that's a great question. Perhaps I'll answer these two questions in a moment. I won't forget you guys. For more information, you can visit a bunch of different sources. ISMIR is the seminal conference in music information retrieval. This year it's held in Taiwan. It rotates all around the world. And it's really kind of interesting what research you'll see there. So here, ISMIR, October 27th, 2014. Okay, classification. Is this organized? Classification, musical time information, MIDI files, texture and symbolic data, detect common mistakes of flute playing, automatic transcription, audio to score alignment, transcription, symbolic domain, retrieval, as a computer science string problem. So a lot of interesting stuff there. Also, you can visit Murex. Murex is a worldwide contest or they call it evaluation campaign for music information retrieval algorithms. Because in the academic community, people were worrying that researchers would propose their own tiny incremental change and say it's the biggest thing since sliced bread. And for the same reasons I mentioned earlier about data sets, it was hard to compare different algorithms. Murex is the campaign that tries to standardize a lot of the results in MIR. So if you go to the Murex page, you'll see that tasks such as audio classification, symbolic melodic similarity, tempo estimation, beat tracking, key detection, and more are executed here as contests. So you can just submit your algorithm. If there are enough submissions, then they're on the contest. As I mentioned about Karma at Stanford, if you go to the workshop website, you'll learn more about our workshop, and we hope to see you next summer. I will be giving a talk next week at PyData. The beginning third of this talk will be the same. The next 2/3 will be different. So if you're interested in coming to that, 1 block away on Harrison between second and third, I would love to see you there. ICASP is a signal processing conference. Transactions on Audio Speech Language Processing is a journal in IEEE. ACM Multimedia is the seminal multimedia conference in academics. Computer Music Journal, Journal of New Music Research. Emmer, this is you, isn't it? Hi. Look forward to your presentation. Machine learning, integration, music information retrieval. What have you learned? So I think what I studied was in the area of transcription and sparse coding, dictionary learning, focused mostly on non-negative matrix factorization and how to improve those algorithms for real-world musical signals. A lot of the academic examples that you see are very canned and very toy examples, and they don't extrapolate well to the real world. So what I some of the algorithms I proposed and worked on were to improve upon those algorithms, make varieties, modifications of them that are better for the real world. I don't know if that answers your question, but I'd be happy to talk more about that offline. Marcus asks, recognizing the beginning and end of vocals in a song to allow for automatically estimating the length of intro and outro of a song. Very interesting problem. I think this is Marcus in the crowd. Hi, Marcus. Thank you for the question. This is something like section identification or song structure identification. I think there was like a funny meme going around Facebook that shows like different song structures for different genres, and it's so formulaic when you think about it. Depending upon how structured the instrumentation is from section to section, it's something that you may be able to infer using the right algorithm. In other words, finding the intro and the outro. Just the way you describe it here, without further constraints, I think it will be somewhat difficult to solve, but just using the information that is asked here. But by constraining the problem, it may be tractable. Pros, I think, is not here tonight. Thanks, Steve. You're welcome. Love to know if similarity for video as well. A lot of these can be applied to video, but I think audio has a very nice special structure, a very nice statistical structure that isn't found in the image or video domain. In video, there is a central problem called like scene change detection. If you Google for scene change detection, that is kind of like in MIR what we call section identification, song structure, form identification. And that's what they use, but with completely different features in the three-dimensional domain, which is 2 dimensions more than I'm comfortable with. That is the end of the talk. Once again, thank you very much to O'Reilly for more sponsorship, product placement, but thank you. And I'll be happy to answer any questions you have. Thank you very much.